Okay, here we have a figure depicting the situation very much like what we've seen, kind of summarizing what we've seen. We have a point xy0 down here in the xy plane. We have some change delta y in the y direction, some change delta x in the x direction. Now this rectangle represents part of a plane parallel to the xz plane through the point xy0. Up here we have the point xy, f of xy, a point on the graph of the function f of xy. Now here we have a line segment whose slope, I say, is fy of xy. Now what's that slope represent? Well, it represents how fast the function is changing if we move in the y direction. We call that the partial derivative with respect to y of xy. And it should be obvious that the change in z corresponding to this change in y here, which would be the run of this triangle, is going to be the run times the slope fy delta y. Now, just what does this fy represent? Well, if we slice xyz space with a plane parallel to the yz plane through this point xy0, we get a curve. Okay, and where that plane intersects the graph of our f of xy function, we have a curve, assuming that this function has is smooth, assuming it has derivatives of all orders and so forth, or at least a sufficient number of orders that we have at least the first derivative. Okay, and the slope of this triangle here is just the slope of that curve as it passes through this point. Remember, that curve confined to a plane parallel to the yz plane through this point, and of course through this point. So we multiply that slope, and of course that slope is the derivative of that function confined to the plane parallel to the yz plane, etc. And that is what we call our partial derivative with respect to y, and it's very easily calculated if we have a formula for f of xy. We just treat x as constant because it isn't changing. We take the derivative with respect to y, we evaluate it at the point xy, and now we've got our slope. Okay. Well, we do the same thing in a plane parallel to the xz plane through this point, and of course this point. And this rectangle here is part of that plane, and we have a slope in this direction. And the change in z due to this slope is equal to what? It's equal to that slope times the run. The run is your delta x, so that we have a delta z here, which we call delta z hat, is approximately equal to fx times delta x. Now we could complete a three-dimensional figure here as we've done previously, but we're not going to do that at this point, because what we're going to do is we're going to assume now that we move one unit in the direction from here to here. One unit in the direction defined by our delta x and our delta y, whatever that might be. And we see that our delta x, if this angle is theta, our delta x is a cosine of theta, because here we have the adjacent side of a triangle, a right triangle, whose hypotenuse is 1. And delta y is sine theta. Now, we wouldn't actually try to predict the change in the value of our function over a distance of 1 unit unless we knew that the derivative was changing very slowly. Okay, that the second derivative was small enough that the derivative would not change much over a distance of 1 unit. That's not generally true. Hardly ever would it be true for the kind of functions we usually look at. Well, in some cases it might be. So we wouldn't really try to use a distance of 1 here. But if the second derivative was small enough, if the derivatives didn't change by much over this distance of 1, then we could actually use this picture to predict the actual change in the value of f. rather than the change approximated by assuming that the slope stays constant in this direction and the slope stays constant in this direction. In that case, for any delta x or delta y where that's true, where the slope doesn't change much, your delta z would then be fx delta x plus fy delta y. Okay, and again, fx delta x is just slope times run, fy delta y is just slope times run, one in the x direction, one in the y direction. Okay, and that's going to equal fx cosine theta plus fy sine theta. Because, of course, as we saw here, delta x is a cosine of theta, delta x is sine theta, again, when the hypotenuse is 1. Okay, so we have fx cosine theta plus fy sine theta. Look at that product. Does that put you in mind of anything? Well, it depends on how many dot products you've done with symbolic expressions, but if I tell you, it's going to be very clear that this is just the dot product of the vector fxi plus fyj with the vector I cosine theta plus j sine theta. I mean, take the dot product. You get fx cosine theta, right there it is. You get fy sine theta, right there it is. Okay, now this vector that we've defined here, that we've found here, or that we have used, is what we call the gradient of the function f of xy. And this is just a unit vector in the direction theta, where theta is implicitly the direction measured counterclockwise from the positive x-axis. So now we have this dot product of something called a gradient with a unit vector in whatever direction we want to move in. We'll get into this stuff motivated by this example and see how useful it might be.